My name is Anthony Kuzub. I am a senior systems designer and chef de projet production systems, solutions d'ingénieur, engineering solutions for the MTIS, Media Technology and Infrastructure Services, ISTM. I can't remember what that one stands for, but with the Canadian Broadcasting Corporation, CBC Radio Canada. My background is in all things audio. Currently, I am the chair of the Toronto Audio Engineering Society, and I'm also chair of the Audio Engineering Society SC 0505, which is grounding and shielding practices for audio signals. So I go very deep into the technology because I enjoy all things about the technology. Audio is going through a bit of a renaissance right now with IP, and I have been asked to speak at the International Timing and Synchronization Forum and be made available to be asked questions about some of the technology I am going to talk about in this little 15-minute preamble. I'm not going to show any slides, so you gotta follow me. And I'm going to try to explain as much as what we're trying to accomplish with audio. Right now, there is a, I'm going to call it a gap between audio, video, and network engineers in terms of broadcast, and that gap is it's closing in. It's very much closing in, and our Montreal project of running an all IP broadcast facility is living proof of that, and we have some success stories to share with that because it's been a fantastic project. But there's a lot of physical things that need to be connected in order to make a broadcast facility. And right now, our preferred method of moving audio and video over any sort of distance, whether it's long or short, is through IP. And we do a mishmash of certain things, but a lot of it is live because we are a national broadcaster that has the mandate to actually deliver content in real time to Canadians for all of these events that are happening across the country. So we have a rather large network that is being transitioned towards IP technology, and that IP technology has, it's not a revolution, it's an evolution. So beforehand, we were dealing with a lot of proprietary codecs and a lot of proprietary vendor equipment that could only speak point to point with, its co-matched partner. But that type of mentality is starting to change because of a new technology that is emerging of the Audio Engineering Society. So the Audio Engineering Society is an agreed upon body. It is a standards body. It is an organization. It is a mentorship program. It is a group of communities. It is a group of like-minded people, very similar to the IEEE, but specifically focused on audio. And the AES has come up with a new IP standard, 2013, but let's just call it new. And we are starting to deploy it across our networks. And we've started to deploy it in certain regional stations, and we are starting to deploy it in certain national stations. And we are learning new challenges, and we are experiencing new things, and we're being introduced to some things that are old hat and old in other industries, but they are new hat in the broadcast industry. So I work out of the Toronto office, but I work very closely with the Montreal teams on certain projects, specifically for control and intercom, and what we attempt to do and what we do on a daily basis is centralize the news. So the regional stations control rooms are actually centralized in Montreal or Toronto for news production. So a lot of that is done with rented lines that we have across Canada. Between the Toronto and Montreal, we have redundancy between the two stations. So our lines are dedicated for our use. But the technology has aged. We were originally using, like I said, vendor proprietary products that performed extremely well. They took a serial digitalized SDI, serial digitalized interface, SDI video signal, and muxed it with other ones through a series of TDMing. But that's starting to change because, well, we don't necessarily need to have proprietary TDM when we start dealing with packet-based video flows. And that's what I'm going to talk about, is the packet-based video flows and the packet-based audio flows. So as we move PCM audio. So when I say PCM audio, my analog audio here is being converted into pulse code modulated bits. And this happens at a very consistent rate. So Nyquist theory, if you want to sample something that is super high fidelity and, look at my little spectrum analyzer there on the side, here I'm talking low and then up high. I can't even whistle that. Of course I can't. But in those higher frequencies where all my little all that little detail is, that's up in the higher frequencies. And traditionally codecs, and I bet you my video codec here was doing the thing, was reducing some of that high end through compression algorithms. In broadcast, we want all the detail. In music, we want all the detail. In news, we want all the detail. So we need to move PCM audio 48K, 16-bit, 24-bit in real time. So you need to synchronize that. And traditionally, SDI was self-clocking. So the SDI signal actually had a clock built into the signal. And some of these devices would also receive a reference. And that reference plus the incoming clock would combine to resynchronize all of these video streams. Sometimes we would also need to have frame synchronizers to make sure that all of the arriving frames simultaneously arrived at some point by delaying ones and pushing back others to catch up to a deterministic timing. So to improve fidelity, AES67 and PCM audio in IP, and I say PCM audio in IP because AES67, I have to credit this to a brilliant engineer, Nicholas Sturmel, Dr. Nicholas Sturmel, who he said it best. AES67 is PCM audio in IP as little chunks and then time-stamped. And so PCM audio in IP is very important because we need to have PCM quality in IP moving from location to location. Like I said, traditionally we were TDMing it. We would TDM a whole bunch of different audio channels together and put that with other TDM and then over proprietary codecs. But now with IP and AES67 being a layer 3 routable protocol, we can now direct it where we need it, how we need it, and in it being either a unicast or multicast, you can use it in a couple different ways. And I will talk a little bit about that during the conference. But right now, we're also trying to build something that is fault tolerant. So not only do we want PCM audio in IP, we also want it to be fault tolerant. So how do we accomplish this? Traditionally, we're running two lines. Sometimes other little things such as all these encoding processes add FEC error correction, but that introduces delay. So we have to have a real holistic view of the fourth dimensional problem of when these signals need to arrive to the right people in all of the right time. So let me back up and talk a little bit more about AES67 and the Audio Engineering Society. So like I say, PCM audio in IP. Well, you and I, we could sit down. All right, we're gonna take PCM audio, and we're gonna chop it up into very small TDM little blocks. I'm gonna put a packet on it, and then I'm gonna get a timestamp, and I'm gonna send it to you. That is the basic idea of AES67. It's you take a PCM audio, you align it with a small amount of PCM audio, a sample. Let's call it a sample of time, and then you want to send it. But you need to have some kind of reference or agreed upon reference. Before, all of our SDI signals were clocked to a master reference clock that the building fed. But now with PTP, well, we have multiple timestamps that deal with it. But we can go down that rabbit hole together. But there were a lot of proprietary solutions to this problem. And there are still proprietary solutions that kind of can play in this AES67 ecosystem. But there is some secret sauce that they would like to keep for themselves to stay competitive in the market. And but some of those solutions do not travel over the internet or over other, longer distances. So AES67 is designed as a standard for audio applications, high performance streaming audio over IP, and it's all about interoperability. The AES67 and the AES and the Audio Engineering Society, it's all about how it works together. When you had a microphone connector, the pin configuration, that's the Audio Engineering Society. We want to make sure that this device plugging into this device is working. So we relied on RFCs. The Internet Engineering Task Force was instrumental to making this happen. The IEEE and our references to PTP and how PTP 1588 is used to synchronize these packets and timecode these packets. We leverage the things that have been done. There's a great adage. A fellow by the name of Neil Munsey said to me. He said, if you want to solve a problem in audio, you have to look to the telco because they solved it 20 years ago. And he's not wrong at all to this date, because the telco went to IP and went to RTP traffic, and so we, as the AES Engineering Society, have to work on the shoulders of giants and leverage that technology. So RFCs were introduced to align the transport mechanisms. But RFCs were also introduced to align how these devices connected to one another and what clock they referenced and what type of clock is what type of clock is it following, or does it even have a master clock or a PTP reference clock? So these session description protocols carry timing information and information about the stream and the session. So there is now some more discussion about, how do we actually move this stuff from large distances? How do we move it from Toronto to London and London back with zero latency using this technology? And AES67 has the mechanisms built into it to actually handle this type of transatlantic transmission. It can accommodate this with a couple of unique twists, and I believe the Audio Engineering Society, along with manufacturers and scientists from around the world, are currently working on a document that explains how you can move AES67 across privately controlled networks and networks that you have control over. A lot of this technology is very common in the world of IT, and it is very common in the world of network engineering. So this RTP load is, a language that is well known. The big challenge of broadcasters and engineers in broadcasting is this language between the two. But of course, the Audio Engineering Society also worked extremely close with the Society of Motion Picture Television Engineers to make the audio AES-67 and the streams parallel to the video. So there's a new technology called SMPTE ST2110, and one of the subsets is ST2110-30. And that's the video format that we have installed in the new MRC. And I will be able to talk a little bit about that at the conference. I look forward to participating and learning from colleagues around the world. Take care.